Hello, welcome back to Discrete Calculus with the Wolfram Language. I'm Alistair Forsyth, and today's video will be going over prime numbers. A prime number is an integer greater than 1 whose only positive factors are 1 in itself. In other words, an integer greater than 1 is prime if and only if its only positive factors are 1 and itself, such as 2, 3, 5, 7, 11, or 13. Here we have that written out in some slightly more complicated notation, but this is just saying for any x that is an integer, and x is greater than or equal to 2, x is prime if and only if there does not exist a y that is an integer, such that y does not equal 1 and y does not equal x, but y divides x. Two numbers are coprime if they share no common factors other than 1, like 25 and 12. 25 has the factors 1, 5, and 25, meaning that it is not prime in and of itself. But 12 has the factors 2, 6, 1, 12, 3, and 4, meaning that they share no common factors, making them coprime. In the Wolfram language, prime of n gives us the nth prime number. Here, we use this to write out a table of the first 10 prime numbers, 2, 5, 7, 11, 13, 17, 19, 23, and 29. Using this, we can also make a table of the gaps between any prime number and the next. If we plot that gap as n increases, we can see that the change between any two prime numbers increases as n increases. However, if we plot the relative change between two prime numbers, it actually decreases as n increases. Here we use some code to plot out the natural log of the nth prime number as n increases. You might be able to see a bit of correlation between that and the gap of n as n increases. This is actually because the gap between the nth prime number and the n plus 1th prime number actually asymptotically approaches the natural log of prime of n as n increases without bounds. Along with that, we have a couple various primality tests in the Wolfram language. Here we have prime q of n, which returns whether or not a number is prime. Given a random prime number, it'll always return true. We also have coprime q of n, k, which tests if n and k are coprime. Given the two prime numbers 17 and 11, it returns true, because all prime numbers are coprime with each other. We also have composite q of n, which tests whether n is a composite number. Here, I gave it a random number, and it returned true, because 187 is composite. Looking at some notable properties of prime numbers, we have Bertrand's postulate, which says for any integer n greater than 3, there exists at least one prime number between n and 2n minus 2. Taking this and making it more general, we can say for any integer n greater than 1, there exists at least one prime number between n and 2n. And all of this was proven in 1852. Another property of prime numbers is the prime number theorem. To properly explain this, imagine a function pi of x and let that be equal to the number of primes less than or equal to x for any real number x. The prime number theorem states the limit of pi of x divided by x over the natural log of x as x grows without bounds is equal to 1. This means that for the nth prime number p of n, as n grows without bounds, p of n asymptotically approaches n times the natural log of n. The prime number theorem also states that the average gap between the nth prime number p of n and p of n plus 1 will asymptotically approach the natural log of p of n, as we saw earlier. And even though this was proven in 1896, we can also demonstrate it using functions in the Wolfram language. Here, we look at the asymptote of prime pi of x as x approaches infinity. Now this comes out to be x over the natural log of x, which is copacetic with the prime number theorem. We can also take the asymptote of prime of n as n approaches infinity, which comes out to be n times the natural log of n, as stated by the prime number theorem. One of the most common uses of prime numbers in our modern day is cryptography. Now there are many different encryption algorithms out there, but to demonstrate how prime numbers could be useful, I wrote out RSA encryption in the Wolfram language. To start with, we take two prime numbers, p and q, and compute their sum. Taking the 18th prime number and the 16th prime number, that sum comes out to be 3,233. Then we take Euler phi of n and two integers u and k. U must be less than and coprime with Euler phi of n. Here we use k to create a private key that is equal to 1 mod Euler phi. Computing this, we get an Euler phi value for n of 3,120, and we can see using coprime q of u, Euler phi of n that they are in fact coprime. And we compute our private key to be 2,753. This piece of code gets our data by taking a phrase, in this case it's secret, and computing it into character code. Then we encrypt it by taking that data raised to the power of u taken mod of n. We can see that our original character code is quite different from our encrypted character code, making it essentially unreadable if you don't have the private key. Then we can decrypt it by taking the encrypted value raised to the power of the private key mod n. And this comes back with our original character code, only using the encrypted values and the private key. Now the reason this requires prime numbers is that Euler phi of n is quite hard to compute unless you use the sum of two prime numbers. Euler phi of n simply returns the number of positive integers that are less than n but are relatively prime to n, meaning that if you take Euler phi of n, where n is the product of two prime numbers, let's say p and q, then it will return p minus 1 times q minus 1. We can confirm this is true using the Wolfram language, taking Euler phi of n equals p minus 1 times q minus 1. Here you're effectively using prime numbers to limit the value of Euler phi. Now here's a little artifact from when I was creating this presentation. Originally I tried to type out a random composite number to show that the factor integer function in the Wolfram language returns all the factors of a composite number. But I accidentally, by just slamming my fingers on the keyboard, typed out a 9-digit prime number. And for reference, I can confirm this twice in Mathematica, that this is in fact a prime number. And the chances of that happening, given a random 9-digit number, is about 1 in 2,000. So it's kind of an interesting little get there. Anyway, to demonstrate prime factorization, I wrote out some steps for prime factorization. First, we take an input and set our guess for the first prime factor at 2. Then we go through a loop where if our guess divides the input, we write down that guess and start again with the quotient as the next input. If it doesn't divide the input, then we change our guess to the next prime number after the current guess. If our input is ever less than the guess squared, then we just write down the current input. If you do those steps and write down the guess and the inputs where appropriate, you should end up with a list of the original input's prime factors. Something to note here is that the fundamental theorem of arithmetic says that each positive integer has a unique prime factorization that only applies to it. So if you take two inputs that are different, you'll never get the same prime factorization. We can also use some functions in the Wolfram language to do this for us. For example, the factor integer function, or the prime q, composite q, and coprime q functions that we talked about earlier. Here, we could go through these steps over and over and over again to get the prime factorization of 9,603, or we could just use the factor integer function in the Wolfram language to get it immediately. Here, it retrieves 3, 2, 11, 1, and 97, 1, because the prime factorization of 9,603 is 3 times 11 times 97. Now, a big problem in our modern day relating to prime numbers is the generation of prime numbers. Generating the nth prime number for very high values of n can be very time-consuming and difficult to verify. One method that people use is prime sieves, which essentially take a large number of inputs and then repeatedly go through and eliminate each input that is composite, leaving you with a list of many prime numbers. Another modern method are probabilistic tests, which take a given number and test if it is prime by comparing it with a couple different inputs. Not only are probabilistic tests a lot faster than many alternatives, but they also allow for the user to see the probability of incorrectly determining the primality of a given number n, which is helpful because it means you can repeatedly iterate the test using different inputs to get a higher probability of your test coming out correctly. Thank you for watching. Today we went over prime numbers, some of their notable properties, such as the prime number theorem and Bertrand's postulate, and we went over some of their real-world applications, like the RSA encryption algorithm. In the next video, we'll go over another important sequence, namely the Fibonacci sequence. For further details, you can check out the reference page for prime numbers on Wolfram Math World. Thank you for watching, and I'll see you in the next video. Bye-bye.